Welcome back. So I hope that you remember everything about correlative sparsity. And if you don't, there will be some small exercise sessions to refresh your memory. So yesterday I talked about these correlations between the variables, and which is called correlative sparsity. And today I'm gonna talk about term sparsity. So the first idea of term sparsity in the context of polynomial optimization was developed by Reznik in '78. So at the time there were no SDP solvers. Convex programming was not as developed as today. And so who doesn't know what this Newton polytop is? Okay, so everyone knows about that. Okay, so it can be maybe a bit quick. So you take a polynomial. So here, this polynomial f has 4 terms. Then you draw the support. You take the convex hull of the support. This is the Newton polytop. And then Reznik has this powerful result that tells you that basically you can shrink the Newton polytop by half. So you get half of this triangle here. Then you take the lattice point, and you know that every square, if f has sum of squares decomposition, every square is supported in this shrinked polytop. So for this example, you have a polynomial in degree 2 with of degree 10 with 2 variables. There are only 4 terms in the support of f, and then you know that you can index your moment matrices, or here it's the Gram matrix with only 5 terms. Okay, so in general. So in general, when you want to index with all the terms, you have the vector of degree d of all terms. So you have 1, x1, x2, x1 square, x1, x2, and so on, up to x2 power d. And you know that f is SOS if and only if there is a so-called Gram matrix associated to f with non-negative eigenvalues, such that f is equal to this vector of monomials times the matrix times the vector of monomials. So there is an equivalence between being a sum of squares and having this decomposition. And then, well, it's a certificate that f is non-negative, because since G has non-negative eigenvalues, then the product is non-negative. But then what you can try in practice is to replace this guy by a smaller vector. And this is exactly what happens here with this Newton polytop trick. So here we have a matrix. Of course, I didn't take the same notation. So this matrix here is 5 by 5 instead of so G plus n, choose n. Okay, so 5 it's nothing, right? Okay, so this is the basic idea, and then you can do quite some stuff with this, especially if you want to optimize polynomials without constraints. And so this is the basic pillar of what we developed with my former postdoc Ji Wang, so this so-called term sparsity technique. So at the beginning, you start with this Newton polytop trick. So here I took another polynomial. Here the matrix Q is a 6 by 6, so the number of unknown entries is 6 plus 1 divided by 2. And then the story will be quite similar to correlative sparsity. So you will build a graph, but in this graph, each node, instead of being a variable, will be a term. So here there are 6 terms, so there are 6 nodes. And then you draw an edge between 2 nodes if the product either appears in the support of f or is a square. Because at the end you want sum of squares decomposition, so you also have to include the squares. So for instance, here on this graph, you don't have, so you have an edge between x2 and x2, x3, because x2 square, x3 appears in the support. Where is it? Here. Okay? but you don't have an edge between 1 and x2 because x2 is not in the support. So that's pretty easy construction. And then as for correlative sparsity, if this graph is not chordal, you make it chordal by adding the proper edges, and then you compute cliques and so on. Okay? So the story is very similar, but instead of indexing by variables, you index by terms. That's why it's called term sparsity. So here, if we index this matrix by this graph, then the number of non-zero entries is 6 because you will take the nodes, so it's the diagonal elements, so you have the squares of these elements. And then you have the entries corresponding to the edges, so there are 9 edges in total. So the number of entries is 15 instead of 21. And then if you do the clique decomposition, you can retrieve somehow the same number of entries. So here, for instance, you can take the clique 1, x1, x1, x2, and then x1, x2, x1 and x2, and then x2, x3, x2, x3, the product x2, x3, for instance.
So at this stage, is it a heuristic or is it?
Yes, it's conservative relaxation. Yes.
And if you apply it to the statistic component, you get the same over.
The same what?
The same support B over.
Well,
For the statistic component.
so the size of the matrix is the same. So it's going to be a 6 by 6 matrix, but the number of non-zero entries will be different. So here the number of non-zero entries is 15, and in the first example, it's so at the beginning you suppose it's 21. It might happen that after solving, some entries are zeros, but what you assume at the beginning is that you have 21 non-zero entries, and then here with this graph it's 15, without using the clique decomposition. Does it answer the question?
I don't understand your answer. So the basic component you are
Yes.
polynomial on the previous slide.
Yes. Yes.
So you apply it here.
Oh, you mean if I apply the term sparsity here? I don't know. I didn't do it for this one, but yeah, I guess you have a graph with 5 nodes, and then you have a certain number of edges. That's a good exercise for later on. Okay, so this is the basic ingredient. And then, so the good thing is that, so the Newton polytope stuff, it doesn't really work for the constraint case, because you can have some cancellations in the sum of squares decompositions. But this construction, based on this term sparsity pattern graph, works in the constraint case. So at the beginning, what you can do is that you take this vector of monomials. So you take everyone, and then, again, you draw the graph and the chordal extension of this graph. And so here the condition on the support is a bit more complicated because you need to check that potential products appear either in F or in the GJs, so one of the constraints. And of course, also you need to add edges if you have squares. So it starts quickly to be complicated. So I will show you some graph examples, but it might be hard to see why it works immediately. So here, this is an optimization problem with 2 constraints, and the term sparsity pattern graph looks like that. So for instance, I hope I will be right. So you don't have an edge between x4 and, okay, but there is x2, x4 here. So I don't know, maybe there is no edge between x3 and x1, x2, because x1, x2, x3 does not appear in the support, for instance. So it's the same in the constraint case, basically. It's the same construction. And then, of course, you can stop, and it's a heuristic, or you can add more edges if you want. So how do you add more edges? Well, you say that if I have a product which is present in my support, it's because it's a product of two terms which index my matrices. And then I can say, okay, maybe I can obtain this product in other ways by multiplying two other terms. Then you're going to say that you're going to add these nodes to your graph. And so you're going to connect all the terms whose product already appear in the graph. So for instance, here at the beginning, you have an edge between 1 and x2, x3. But you don't have an edge between x1 and x2, x3. But here you have an edge between x2 and x1, x3. So x1, x2, x3 is there. But then if x1, x2, x3 is there, then you can connect x1 and x2, x3. So the resulting SDP variable corresponding to this x1, x2, x3 will be the same. So you don't add new SDP variables to your problems by doing that. It's free, okay? But then since you added edges, the resulting graph might not be chordal anymore, so you can take the chordal extension, and so on and so on. So you obtain an iterative process where you basically add edges and at the end converge to something. And this something is good. It corresponds to the dense relaxation value. Yes?
One question. As long as I have one as a node, I can basically draw edges all over, right? Because
no.
Polynomials exist. I don't understand why.
No, because it must exist in the support. So for instance, if x1 is not in the support, you will not draw an edge between 1 and x1.
Okay. But then I thought if x1 is a node, then x1 exists.
No. If x1 is a node, it means that when you multiply it with some other node, then it's in the support. So if x1 is isolated, yes. x1 is, even if x1 is alone, it might not be in the support because you need to take the squares. So it means that basically you allow x1 squared to be in the support.
Second question. So
yes.
when I do the chordal extension, there are many ways to do chordal extension.
I will talk about that in a moment. And if it doesn't answer your question, we can discuss again. Okay, so T-SOS, term sparsity, is a hierarchy within the hierarchy, where you start from a potentially very small graph, and then you complete it by relying on this two-step iterative process. So you alternate between support extension, so possible degrees, possible products with several terms, and chordal extension. So you have a two-level hierarchy of lower bounds, which is indexed by the degree of all possible monomials, and also the number of two-step iterations that you do. So sorry in advance, the notation will be a bit messy, but you need to take into account these two relaxation parameters. Any questions on that? Yes?
So when you have such successive extensions, do you have a way to reuse some of your computation at one stage in the next one?
I guess so.
Thank you.
So yeah, so I didn't really talk about the algorithmic aspects of computing the chordal extension. So in practice, we use very fast heuristics. We have the right software libraries to do that. I think this is something that Tobias mentioned yesterday during his talk about symmetries. So at the beginning, you want to solve an NP-hard problem, right? So all the hardness of the problem is translated to computing these chordal extensions. But there are fast heuristics to do it. Okay, so I showed you a little bit how it works for the SOS side with the graph matrices. In the moment side, it's pretty similar. So you build the chordal extension of your graph, then you compute the maximal clicks, and then you replace every condition on your moment matrices by several conditions for each click. So every moment matrix is indexed by a click. Okay, so you replace one conditions by these click conditions, and then you do the same, of course, for the localizing matrices. So you have a different graph for the associated to the constraints, and then a lot of indices for each constraint and for after a certain number of finite iterations. Okay, so this is the moment hierarchy exploiting term sparsity. So here you have the moment, the pseudo-moment constraint, and here you have the localizing constraint. And if you look at the dual of that, it's the so-called TSOS hierarchy. So term sparsity sums of squares. Okay, and it's a two-level hierarchy. So what does it mean? So here it's the first thing that I showed you before with the first graph at the minimum degree. Okay, and here when I go to the right, I build more and more complicated graph, but I keep the same degree. So potentially here, I will have the dense relaxation. So what would correspond to the dense relaxation. And when I go from top to bottom, then I just increase the degree, but I take the same number of graph iterations. And here there is f min somewhere, the minimum of f.
Somewhere or at the limit? It's somewhere or is it at the limit?
It's at the limit. So this thing, you get it after infinitely many iterations, because at the end you complete the graph in the worst case, right? Here you might have to go to infinite number of steps. Okay, so to answer the question about the choice of chordal extension, so there are many choices, and this will have an impact on the performance and on the accuracy. So this is what we call approximately minimal or minimal fill-in in the graph theory language. So here you take the minimal number of edges to make the graph chordal, and you can also take everyone and have a complete subgraph. So we call that maximal chordal extension. And depending on the chordal extension, then you have more or less theoretical guarantees. So if you fix a sparse order, so a number of graph iterations, then you have a sequence which basically increases. So you get better and better accuracy. It's not surprising. If you use the maximal chordal extension, then you can show that you converge to the dense value. So it's not conservative anymore. And in the worst case scenario, you would have a number of terms corresponding to the dense case, but actually it's a bit better than that. So actually, the structure that you obtain at the end corresponds to exploiting sign symmetries. So it's a bit shocking at the beginning, but it's like that. So exploiting term sparsity at the limit is the same as exploiting sign symmetries. So if there are no sign symmetries in your problem, then you obtain the dense hierarchy. And if there are some sign symmetries, then you obtain the block diagonal decomposition corresponding to sign symmetries. So if you use the maximal chordal extension, and if you start with the monomial basis. If you don't start with the monomial basis, so for instance, here if you start with the Newton polytop vector, then you can get a smaller decomposition. And I will show you an example. So here there are 1, 2, 3, 4, 5 terms in the Newton polytop. So this guy f is invariant under flipping the sign of x2, okay? Because here we just have a not power to x1. So this guy is not invariant under the flipping the sign. This guy is invariant, this guy is not, and this guy is invariant. So when you exploit sign symmetries, you put all the invariant guys together and all the equivariant guys together. So you obtain two blocks. So these two blocks are here. And so this is the decomposition that you obtain by exploiting sign symmetries. And when you do term sparsity, starting with the Newton polytop, at the end you obtain not 2 but 3 blocks. So it's sparser, it's a bit sparser than sign symmetries. And in this case, you get the same bound when you do the optimization. So,
So this is, this is kind of a bit surprising because I didn't really like or maybe I don't really understand the semantics. So what's the meaning of chordal extension in this case?
So chordal extension means that at the end the graph is chordal. So it means that every cycle of more than 3 nodes has a chord.
No. I understand perfectly the graph chordality of things. What's
Okay.
the meaning with respect to the actual system we started with? Because this relates to why sign symmetries appear, I guess, here. I mean, at least in my head. So I can't get a meaning of what it means, actually.
So the reason why it converges to sign symmetries is because at the end, so your graph will stabilize at some point. It will either stabilize to, if you are not lucky, it will stabilize to the complete graph. And in other scenario, it will stabilize to this setting. And this stabilized graph is invariant under the support extension. So you know the support extension is the fact that every time you have a product, you will look potentially for terms such that when you multiply them, you get the same product. And then you realize that when you do this thing, and you have a block, all the guys from this block have the same sign symmetries. So you do a case analysis, and you realize that because of this closeness under support extension, all the guys from one block have the same sign symmetries. And then you prove the opposite direction, and then it corresponds to sign symmetries.
So isn't it because you also take the square?
Yes, of course. Does it answer a bit more?
Yeah.
And but this is only true. So this is only true that you get the sign symmetry stuff if you start from the monomial basis. If you start from another basis, so this vector of monomials given by the Newton polytop, you can have a sparser thing. So here you have the same block of invariant guys, but then you split the equivalent into 2 blocks.
Can you explain again how this block has been split?
Which ones?
The last line.
The last line? Okay, this line is clear?
Yes.
Oh, you mean how do I obtain that? Well, I apply this algorithm. And so I check if 2 terms, when I multiply them, it's in the support and so on. So that's another thing that I wanted a message that I wanted to give. So if you are not lucky, doing term sparsity is the same as exploiting sign symmetries, if you are not lucky. But in practice, we will be very lucky, very often. And then there is, of course, a conjecture that if you take the action under a finite group, or a group like the one that Tobias showed you yesterday, so you have a block diagonal decomposition of your SDP matrices at the end. Does there exist another term sparsity hierarchy that would converge to this decomposition? So this we don't know. Okay, and then I also wanted to talk about competitors. So I already talked about them a bit yesterday, but so I mean they are colleagues, but so some colleagues reinventing somehow these techniques based on diagonal dominant matrices, but transpose that to the world of polynomials and in particular sums of squares. So this is completely heuristic. There is absolutely no guarantees of convergence. So the idea is the following. So you don't want to pay the cost of finding a matrix satisfying that, or it's also written here. It's exactly the same thing. Because there are too many variables, the size of this matrix is too big. So what people do is that instead they say, oh, okay, I'm not going to look for a matrix which satisfies that. I'm going to look for a matrix which satisfies that and which is diagonal. Why not? Or which satisfy this diagonally dominant condition. So every diagonal entry is greater than the sum of the other guys in the same row and the same column. Or equivalent to a diagonally dominant matrix. So it's cheaper because instead of solving a semi-definite problem, you solve a linear problem, or here you solve a second order problem. But of course, this matrix might not exist. So it's like that. It's kind of heuristics. And of course, when we wrote the first paper, people say, "Ah, but you didn't compare to this thing, blah blah blah." So we compared it. And so what happens is that it's quite easy to prove that the very first relaxation, so the one which is here, is always better than this. Okay. But it might be more expensive. Because here you solve an SDP and not an LP or an SOCP. But in practice, it's not slower, it's about the same. So this is comparison with competitors. Yes?
We need linear programs because we neglect the entries outside the diagonal?
No, you don't neglect that, but so you just write these conditions, right? There might be a mistake. Maybe there is an absolute value here, but it's the same. Just add more variables to encode the absolute values.
I mean, it's not a bad idea. If there is a good reason to think that the matrix Q has a particular form, it makes sense to restrict to those kind of. But if it's picked randomly, then yeah.
Sure, but very often this is captured by that. And also this thing only works in the unconstrained scenario. I mean, you can also try it in the constrained scenario, but it's very ad hoc, it's very heuristic. There is absolutely no reason that it will converge. And then there was a fight between some other colleagues. There was an archive fight about the fact that it doesn't converge, and it was pretty funny. I was not part of this fight. No, but I mean, yes, of course, you want to try every heuristic to solve your problem. I'm not sure it's the best one, though. Okay. Any questions on that? Yes.
There is something that is not heuristic in the literature on choosing monomials. Like also in your even in some toy cases, degree 2 in few variables. Can you say this is the right monomial to choose? Like, or this is the right chord to choose?
No.
If you could do it, you would be.
So. Yes. So basically, what we do is that if we don't have much computational power, we take the minimum, the approximately minimal chordal extensions. If we have a bit more power, then we take the maximal one. But then sometimes you are not happy with the bound, so you go to the next step and you just try. But it might not be the best choice of monomials, and there might also exist other term sparsity hierarchies, right, associated to other groups. So, yeah. Yes, equivalent. Yes, exactly. Yes. Yes.
So you motivate term sparsity by the objective to reduce the size.
Yes.
But it could be interesting to split into blocks. To have many, to increase the number of blocks.
Of course, you can.
Which would be more efficient than reducing the size. So you know there are techniques for that.
But at the end, you take blocks, right? You take the clicks and you index every matrix, every block matrix by a click. But what do you mean? You mean split again the blocks? Yes, of course you can try. Yes. Just need to be. I don't know, but you need to be cautious when you do that. You need to be consistent, have the same pseudo-moment variables and so on. But yes, you can do that definitely. Sometimes taking random subsets also works. There are papers, for instance, on the max cut problem where they do that. They have several heuristics to choose randomly these blocks. And sometimes it works, sometimes it doesn't. It's completely magic, yes.
Just for the second option, actually.
Yes.
But isn't it, I mean, it's the case in general that if your matrix is like simply positive, it's like a U diagonal matrix, U transpose.
So every SDP matrix is not necessarily diagonally dominant or equivalent to a diagonally dominant matrix.
For the first line, I agree. For the second line, I mean, you can always diagonal asymmetric positive symmetric matrix, like U, sigma, U star, with U like having the eigenvalues, which is all positive. So, it is diagonal dominant.
No, I. Yes, but it's not the same. We need to see after, but it's not the same. And I think there are counterexamples where there exists an SDP matrix, but not an equivalent diagonally dominant matrix, for sure. Okay, and then of course you can do the combo. So you can first apply these correlative sparsity techniques, and then apply term sparsity techniques. So first you partition the variables with the techniques from yesterday, and then on each block you apply these term sparsity techniques. And then again you get a two-level CST source hierarchy. And now I'm gonna show you a lot of graphs, just to give you insights of what's happening when you do either correlative or term sparsity or the combo. So here, I'm going to do the combo. So I'm going to start with correlative sparsity. It's a 6-variable problem. Also for those who missed the course yesterday, you can have a brief reminder about correlative sparsity. So here I draw edges when I have a product of variables appearing in the support. So for instance, no x1, x4, because I don't have the product x1, x4. Okay, so this is the exploitation of correlative sparsity. So at the end, I obtain a graph with two clicks. So one with 1, 2, 3, and the other with the 4 nodes here. So which is a complete subgraph. And then I'm going to apply term sparsity. So first to 1, 2, 3. And so this is the graph I obtain after doing that. So nothing particular. So again, there is no connection between I don't know 1 and x1 because x1 is not there. And then you do the same for the second click. So you get this graph. Good. And then you can also apply term sparsity without correlative sparsity. So you directly apply the term sparsity thing to the initial polynomial. And as you can see, you don't obtain the same graph. So this graph is bigger, so it will be more expensive to solve. Okay? Because so instead of having this, then you have this more complicated graph here. Then these guys were already there. And I think this guy, yeah, I think it's the same as this one. So it's better to do the combo. Yes?
I have a naive question.
Yes.
You take examples with 6 variables so you can draw the graphs, but for those sizes, are the number of vertices really a problem for implementation?
It depends the degree you want to go. So degree 2, 3, 4 is fine, more or less, but then it's hard to solve. with a laptop like this one, standard laptop. Any more questions before I go to applications? Yes.
So when I complete, what happens if I try to minimize the maximal size of the component when I do the chordal completion? So if I go for the, so you mentioned that there are many ways to do the chordal extension.
Yes.
But one particular way actually is interesting, at least from the graph theory point of view, is to minimize the maximum size of the tree, to compute the tree width basically.
Sure, this is what the minimum fill-in does, I think. Yeah.
So
you want to, so just to be sure, you want to minimize the maximal block size.
Yes.
Yes.
So I was wondering, could you comment on what is there any particular how can I put it? Is it more interesting actually to go with this minimum fill-in compared to the dense one or compared to the others? Or
So
we don't really know.
So it depends. So the problem if you don't do the maximal chordal extension is that you might get a bound which is looser, which is coarser. So it's a trade-off. It depends. I will show you some examples at the end. You will see that you can't really predict in advance what's going to happen. Okay, so this is one application of sparsity. So it's the optimal power flow problem. So I will not explain what these equations are. So the only thing I wanted to highlight is that it's a very complicated problem. So you want to minimize the active power of an electrical network under the physics constraints. So you have this conservation law, the Kirchhoff laws, the Ohm laws. And the unknown here are the voltage variables. So SG are active powers, and Sij are power variables that will play a role when you will write your conservation equations, so the power flow equations. So this problem is horrible because the variables are also complex variables. So actually every time you have one, actually you have two when you go to the real case. And then you have some nice constraints here that every voltage should be bounded in order to avoid the system to explode. And you also have some bounds on some angles of products of voltages. So there was a thesis by Cedric Josse where he applied correlative sparsity techniques to instances of this problem. And then you can go up to 2,000 variables for some instances. This is still an open problem to solve this minimization problem with a gap close to 0%. And so this is a small benchmarks to show you a bit what kind of results you can obtain for this huge nonlinear problems. So here this is the number of variables. So at the bottom you have a problem which is nonlinear with thousands of variables. This is really huge. And this is the number of constraints. So here you have tens of thousands of constraints. And of course there is no mystery. So if you want to solve this problem, you have to solve an SDP with a size which is about the same as the number of constraints or the number of variables. Because otherwise you cannot solve the SDP with modern laptops. So what is the gap? So the gap is simply obtained by local methods, local optimization solvers that give you some kind of feasible point, because very often the local solvers also lies. Especially if you do some scaling tricks, you can have very weird behavior of these local solvers, but whatever. So the local solver gives you an upper bound, and the hierarchy gives you a lower bound, and then you compute the difference between these bounds, and this gives you the relative gap. So here, for instance, for this first problem, the gap is quite small. It's quite satisfactory. If you apply just correlative sparsity, you have some blocks of size more than 60. If you do the combo, then you divide the size of the block by 2, so also the computational time. But here you see that the bound is less accurate, so the gap increases. Okay. Okay, and this is also something that we have here on this benchmark where correlative sparsity works. So you have a higher gap. But then for the other problems, well, you can't do anything even after applying correlative sparsity. So you don't have the choice. So and here, so here we are lucky. So of course there are benchmarks where this works terribly bad. Huh? I didn't show you, but you have gaps of 15–20%. But we don't know how to solve these instances. But okay, these ones we were happy, especially the last horrible problem, which comes from our company RTE, which distributes the electricity in France. Any questions on this table? Okay. Yeah.
Do you have an explanation why some instances are tied for this velocity?
No. Yes.
So the relaxation order is 2, so meaning the moments are very
4 at most, yes.
4.
And here I took the very first TSOS relaxation, so it's in the two-level hierarchy. This is the number from the top left. I mean, not from the top left. Yes, from the top.
So I suppose you try to increase it with
It crashes immediately. So, no, of course, for this kind of problems, we don't have an explanation. Okay, so this is another application to large non-commutative optimization problems. So this is a collaboration with actual physicists from Barcelona at ICFO. So they are interested in computing the ground state energy of some system, so with particles. So here we have spin states with 3 coordinates. And they can be arranged in different kind of lattices. So you know lattices better than me, I think. But this is 1D lattice. This is a 2D lattice. This is a more complicated lattice arrangement called Kagome lattice. So here you can apply correlative sparsity because you have a chain graph. As soon as you make that into a cycle, you cannot apply correlative sparsity anymore, so the resulting graph is not chordal and so on. Here it's more tricky to apply correlative sparsity and also Kagome. So basically here also we do some kind of combo. And actually even the 1D lattice example is hard to solve. And yeah, so of course if you make it a cycle, then you obtain these so-called periodic boundary conditions, and it messes up correlative sparsity. Okay, so here also we have some kind of local techniques that give you upper bounds on the minimal eigenvalue. So this is a quantum analog of Monte Carlo. So don't ask me exactly what it does. I wouldn't know very well. And also some variational algorithms. So they give you upper bounds, and with the hierarchies, again, you get lower bounds. So you take the minimal energy in sandwich, and this is the kind of results you obtain. So the top graph, the red curve, is the upper bound on the minimal energy, I mean up to numerical errors. And the other curves correspond to various lower bounds. So the blue curve is the one corresponding to degree 4. And this curve here, the one which are very close to the red curve, they correspond to a high degree relaxations. And so just to give you some numbers, so if you try dense at relaxation order 4, with 100 variables, so it corresponds to this number of variables here, then you have billions of variables. So today, modern server on a modern laptop can handle maybe 10,000 or 100,000 of variables. It's way too big. And so the sparse analog can be solved in 1 hour on some cluster from local cluster from the lab. Okay. Okay, and then I have more quantum examples. So I mentioned these Bell inequalities, these linear Bell inequalities in the first part of the talk. So there was this interpretation in terms of maximal eigenvalues. There is also an interpretation in terms of maximal trace. But so actually the idea is always the same. So you have a quantity. So you have this represents some measure, this linear combination of tensor products. A is for Alice, B is for Bob. And then depending on the kind of states psi that you take, you will obtain some values, which can be greater than 2 if you take some quantum states. Okay? So if you take some separable states, then you obtain at most 2. And if you take entangled states, then you can have more. And this corresponds to the so-called Tyrelson's bound. So the maximal violation is 2 square root of 2 minus 2. And then there is a trick to see that this is a tracial optimization problem. So you can prove that if you take an entangled state psi and you apply it to this tensor product, then it's the trace of the product. So this can be proved. And then basically what's going to happen is that you're going to replace all these guys by trace of products. So you obtain 2 square root of 2 by maximizing the normalized trace of this big operator with the classical unitary constraints. And in this case, it also corresponds to an eigenvalue because you have this density matrix argument, and so this is either a maximal eigenvalue or a maximal trace problem. Okay? Do you have a high-level intuition about that? Okay. So, and then there are nonlinear variants of these problems. Basically, this corresponds to taking the expectation of this operator A tensor B. But then you can also consider covariances of these quantities. So there are natural higher order moments of this measurement operator's composition. And so basically, here you have a sum of nonlinear terms. And again, you can take psi as a separable state and check what is the maximal value. So it's 4.5 for separable. But then physicists found one maximally entangled state for which it was 5. Then we thought, oh, okay, let's try to see what happens for all maximally entangled states. So let's compute an upper bound on that. And then if you compute the corresponding dense SDP relaxation, then you find 5. So it means that the maximal value is 5 for all maximally entangled states. And then we also did the sparse relaxation of that because again, you have a very few terms out of the possibly many terms. And it also gives 5 10 times faster. So here we are lucky. Sometimes you are lucky. All right. Okay, so maybe I'm going to skip this part on stability, and I will go to. So I mean, I will still talk about stability, but so what I want to show you is that it works for static polynomial optimization problems, but it also works for the analysis of certain dynamical systems. So there is a quantity that people use in some classes of linear dynamical systems, but with switches, which is called the joint spectral radius. So who never heard about this joint spectral radius thing? Okay, Okay. So it's a generalization of the spectral radius when you have several matrices. So you have M matrices here, and then basically you will compose them with any indices between 1 and M. So you can have A1 and A1, A2, A1, A2, A3, and so on. Then you take a norm. It doesn't really matter which norm you take because it's finite dimensional. Then you compute some kind of geometric average, and you take the max over all permutations. And then you make the number of compositions grow to infinity. That's terrible, and that's terribly hard to compute. And but there are a lot of nice applications. So in particular, if you have a linear system with arbitrary switching, then you can decide if it is stable. You can decide that it's you can verify that it is stable if the joint spectral radius is less than 1. So if you are lucky and you know how to compute this row and it's less than 1, then the system is stable. But of course, it's very hard to do that. It's NP hard to compute and also to approximate this guy. So people, of course, try to approximate it with optimization techniques. And so actually what you're going to, so the high level intuition is that you want to approximate this norm. You want to approximate this norm, and so to approximate this norm, you will take a positive definite function, f, that will do that. And you want this norm approximation f to satisfy this inequality. And then you can prove that if this inequality is satisfied, then the joint spectral radius is less than 1. So in particular, if this guy is 1 here, then here f is some kind of Lyapunov function, because it decreases along the trajectories. Because so this is the application of this is the next step that you obtain after switching to I branch with the matrix AI. And so this is the next iterate. And so this function decreases along trajectories. And this function is positive definite, so it is a Lyapunov function. Okay? So there is a connection between the Lyapunov function theory and this kind of inequalities. And of course, you don't know how to find an f which satisfies this, but you know how to find a sum of squares which satisfy, which corresponds to this inequality. And so basically, this is what we write here, okay? Because so if this is a sum of squares, then this inequality is true. And so there is one way to enforce that f is positive definite. So positive definite means that is homogeneous polynomial which is positive if x is not 0. But then you can simply enforce that by saying that f is greater than the power of the norm with the right degree. So it will enforce f to be in the interior of the SOS cone. But then there is a small issue. So this problem here is not equivalent to an SDP. So why is that? Because here you multiply something unknown, gamma, by something unknown, f. So this is a bit shitty, but it's not too bad because you can do a bisection on gamma. You have only one single parameter on which you do the bisection, so it's not too bad. It's not like multiplying two unknown polynomials together, which is extremely bad. So you do a bisection on gamma plus an SDP, and in practice, it works reasonably well. I mean, most of the time, in any case, most of the time is spent computing this SOS solution. So, okay, and then so so with my former postdoc, we also never heard about this joint spectral radius before. But then some people from control department came to see us and say, okay, can you apply your sparse thing on on this problem. And then we tried. So basically, you take this program here, and you just replace the condition to be SOS by the condition to be a sparse SOS. But the problem is that here you also need to do something on F, right? Because you also don't know F. So you need to fix a support in advance to F. So this is what we did. We took a stupid F. So this stupid F is just a sum of powers of coordinates. Yes. So we start with this initial support, and then we apply our iterative process. So the details are written here. It's really not necessary to try to understand. It's heavy in notation, but it's just for you if you want to have a look later. And so if you replace the dense SOS condition by the sparse SOS condition, of course you get an upper bound on the dense value. And again, after finitely many iterations, you get the same bound as the dense one. Actually, something which also relates to the sign symmetries. Yes?
How did you fix the support? Is it like random? Because I'm seeing xj2 to the power r. Why not taking, I don't know, other monomials for the support or the dense?
So you want F to be close to a norm, right? So, I mean, you can also start with other support. But this one is one example of support for which it will converge in finite time to the dense case. No, but so the problem is not really here, right? The problem is on AI. Because when you're going to multiply x to AI, if AI is not sparse, then you're going to destroy everything. You're going to destroy the whole sparsity. So of course, this only works when AI are sparse.
So is there a way, like a smart way to link the sparsity or the knowledge of the AIs to the support of the F0?
Not really. No, the only smart way we found was basically by doing the recursive iteration by, of course, including the support of AI, the polynomial AIX in the process. And the same works for nonlinear dynamical systems. The support of the dynamics will somehow have an impact on the support that you have for your Lyapunov function. And of course, it will. So of course, at the end, you obtain the block decomposition, which also corresponds to sign symmetry exploitation. So if your dynamics has a lot of sign symmetries, then it will be always good to do that. So, by the way, so exploiting sparsity for dynamical systems, do you know why it's always tricky and it can be very bad? So the high-level intuition is that if you have a dynamical system, if the dynamics are sparse, if the set of initial conditions is sparse, and if the set of terminal conditions is sparse, it doesn't mean that the trajectories will be sparse. So it's a nightmare. Can be a potential nightmare. When everything is symmetric, then the trajectories are symmetric. And here it is what happens basically. So at the end you exploit sign symmetries. Okay. And then we had this application to a closed loop system. So it was actually it was connected to a real-time system problem, where you consider behavior of programs with completed or missed computation. So you have two kinds of matrices, and then you multiply them. So M is called the deadline. And then, as I said before, so a certificate that the system is stable is if rho is strictly less than 1. And then, of course, you can improve a bit the scalability with these techniques. Any question on this joint spectral radius thing? No? Okay. Okay, so then I'm gonna talk a bit about the last kind of sparsity, and then I will show you some small computation. So you might laugh from your, if you have a strong symbolic computation background, because I'm going to use the notion of ideal sparsity, because I will have some kind of easy equality constraints to handle. So I take the easiest possible example, just to give you an intuition of the reduction. So I want to minimize the problem in two variables, and I know that x1 or x2 is 0. So then I stupidly rewrite that with as a sup. So I want to maximize I want the best lower bound of f whenever one of the two variables is 0. And then you can do a case analysis, right? You say, okay, I either have x1 equal to 0 or x2 equal to 0. So I need to maximize both lower bounds in any case. But then what you see is that this guy only involves one variable instead of two. And then you can, as usual, replace this non-negativity condition by a sum of squares condition. And so this is what you do here, but here this SOS condition only involves one variable. Okay? And so this is the general idea. If this set of constraints is not too bad, so if it doesn't blow up, then you will replace a lot of non-negativity conditions by SOS conditions, but in dimension n-1. Okay? So in general, we have these so-called ideal constraints. So here it's easier to start with the complementary set of edges rather than directly the set of edges. So basically in the graph corresponding to that, you connect two nodes if the product is 0. And then you consider the complementary graph. So you connect two nodes if the product is not equal to 0. And then you do very similar stuff as the things that I showed you before. You take the maximal clicks, and then you index everything with these maximal clicks. And here, so it actually makes sense. So if you build the hierarchy out of this thing, the bounds that you obtain, they are always better than the dense ones. They are better. Usually it's the opposite. They are conservative, but here they are better. So why is that? Because actually, you have the support of your problem. So this is the support of your problem, which is big X, and the measure that you are looking for is supported on this set. Okay? But now you can say, oh, okay, I will cut my support in two, and I will take a measure supported here, and I will take a measure supported here. And the solution will be the same, but the relaxation will be stronger because you actually add more variables, so you are meshing your support. And here the same happens, but you are meshing your support with n-1 dimensional measures, because you exploit the fact that one of the variables is 0. So it's always more accurate, but it can be also more expensive. Yes.
So are you doing a case distinction? So if I have, the number of constraints here is exponential, right? If I have
No, not necessarily. Oh, you mean if you have n?
Yes.
Yes, if you are not lucky, it is exponential. But for the application I will show you, it is not exponential. And of course, all these things was developed by looking at this application. But yeah, you're right. In the worst case, you have 2 power n SOS to add. Okay? So the application comes from this thing, matrix rank. So who never heard about matrix? Non-negative rank? No, not. Non-negative rank, completely positive rank. Semi-definite rank. Okay, yeah, okay. So there are some definitions. So for instance, this is the completely positive rank. So you try to write your matrix as a sum of rank 1 matrices, but every entry of the vector must be non-negative. Okay, and then you have a semi-definite rank version where everything is the trace. Every coefficient of the matrix is the trace of a product of 2 matrices, and all the matrices should be PSD matrices and so on. It's terrible. So, and it's terribly hard to compute. For this, there is so basically people sometimes they give upper bounds on this rank for very specific matrices indexed by very specific graphs. But there is no equivalence. There is no known equivalence between the rank, the completely positive rank of this matrix, and a linear program over measures. So here we will just relax the problem, but the relaxation will be in an infinite dimensional space. Okay? So there is no equality here. And so what people, what people did is that basically they take the convex hull of XX transpose, such that X is positive. And the convex hull of this is somehow easier to characterize, but this is a convex hull, so this is a relaxation. Yes?
What are the properties of this round? For example, can R plus be bigger than N?
I think so. Yeah. No.
I mean, the user round is bounded by N, of course, but
Yes.
can it be bigger than N?
No, I think it's also bounded by. Don't ask me too many questions about upper bounds on this rank. So
I mean, it's always possible to write A under this one.
No.
Okay. The question can be well, it can be infinite more.
Yes, it can be plus infinity. Yeah. No. Of course, you need some kind of completely positivity. Okay, so this is the relaxation of the problem. So we don't really care about the details. So in particular, there is this semi-algebraic set here. So we don't really care about these inequalities and so on. I just wanted to show you that we have these ideal constraints equalities here, and this was the starting point of this collaboration and this ideal sparsity framework. It was in the context of the Poema project during the second month of one of the PhD students. But so basically the high-level intuition again is that if you have a decomposition like that, and if A is sparse, then it means that one of the components of this vector needs to be 0. And then you have one of the two possibly candidates, which is 0. So I'm going to show you some benchmarks. Okay, so there are a lot of dots, but what is interesting with this result is that the x-axis. So you take larger and larger matrices. So here you have matrix of size 4, here of size 5, 6, 7, 8. Okay, and then you increase the density of the matrix. So here's matrices are very sparse, and then here they are dense, sparse, dense, and so on. And red is the performance of the dense, and yellow is performance of the ideal sparse. And actually you can see that, well, it's the opposite, right? The more you are on the bottom, the more performant you are. So yellow is below red, so sparse is better than dense, except so up to some point where the density is too big, and then it's better to do the dense. So this corresponds to the question I had. And the other green is some kind of correlative sparsity exploited in addition. But so the bounds corresponding to the yellow dots are always more accurate than the bounds given by the dense relaxations. And if the matrix is sparse, then it's also more efficient. Any question on this thing? Yes.
The kind of constraints reminded me linear complementarity problems because xi, xj are complementary.
Yes, yes, this is another possible application of that. Yes.
Like, have you tried solvers?
No.
SCP solvers?
No, we haven't tried. Also for ReLU networks, it might be also possible to apply these things. Yes. Yes, it's correlative sparsity bounds, but some kind of heuristic correlative sparsity. So here it can be less accurate. But it's always, more or less, always more efficient. Okay, so I'm going to do a brief conclusion about this, just to say that it's not only for polynomial optimization, but also for dynamical systems, for non-commutative optimization. So for non-commutative optimization, there are almost no ways to relax problems. So to get certificates for the minimal eigenvalues, for instance. Although in the commutative world, there are many ways, right? You can do interval arithmetics, you can do Taylor approximations, but in the non-commutative case, basically you only have that. And we have solvers, so I'm going to do a brief demo. And basically, when you are lucky, you can solve problems with thousands of variables, nonlinear problems, which is cool. And we have a book on the topic, which will be out in beginning of April. But it's also available on arXiv. So some further topics. So we are finishing some study about the convergence rates. So we basically stole all the ideas from Lorenzo, Bernard, Lucas, Slot, and others. So we adapted all these ideas in the sparse case. We don't know how to extract the minimizers with term sparsity, so we have started to discuss that in particular with Bernard. And then I thought that maybe this ideal sparsity idea could be generalized to tensor ranks. So for instance, there is also a notion of non-negative rank, of symmetric rank. But I don't know this topic very well. And then there is a big question. So in sparse semi-definite programming, there is a well-studied issue of numerical conditioning. So here the situation is a bit different because you have a sparse SDP, but you have these ankle constraints. So no one has ever studied that, so that would be also interesting. And then there are natural questions of combination with other structure exploitation techniques such as symmetries. So for instance, it's not necessarily clear that everything is, that the two operations commute, first exploiting sparsity and then symmetries, or the opposite. And of course, there are, as I showed you, there are tons of applications, a lot of work to do. So I'm going to show you a quick demo. Yes, it's after that. So there are some exercises if you are interested. So, okay, so this will be a computer assisted proof up to numerics that if you are a sum of squares, if you are sparse, and even if your graph is chordal, so the Renning intersection property holds, then you are not necessarily a sum of sparse squares. Okay, so I'm gonna take these two examples. I'm gonna do some stupid copy paste. So here I'm loading the libraries, which is called TSOS. And here I'm going to set up the variables of my problems. And then I'm going to define my polynomial. So this is a polynomial in 3 variables. It's a sum of 2 terms, depending on x1, x2, and x2, x3. So the running intersection property always holds in this case. And then I'm doing the sum of f1 and f2. And then I'm going to compute some dense bounds and some sparse bounds. So first I'm going to compute the dense bound. So the solution is, so the optimal value is called dense 2. So first time it's always slow because it needs to build a model for the SDP. But then next runnings should be a bit more efficient. So this is just pre-processing time. So here in this case we have around 30 affine constraints. So this is the ugly output of the SDP solver, and this is the bound that you obtain. Okay? So it's 0.84 something. So it means that f minus this number is the sum of squares. And then you do the same with the different kind of sparsity. So first, with correlative sparsity, and the bound that you obtain here is strictly less. So it means that, okay, f minus this thing, 0.002, is a sum of sparse squares, but f minus 0.8 something is not a sum of sparse squares. So this is a counterexample of the fact that every sparse SOS should be a sum of sparse squares. Is it clear?
What should we conclude from the first dense bound? I couldn't.
Nothing. That f minus the bound that you obtain is the sum of squares, and that it's the best possible bound. It's the best possible lambda, such that f minus lambda is the sum of squares. And this lambda that you obtain here is less good, strictly less good. Yes.
Is your drawing approach parametric with respect to the float type? Can you use big float, for example?
No.
Because of the solver behind?
Because we have, so if you know YARMIP in MATLAB, we use some kind of analog of YARMIP, which is called jump. And jump doesn't embed floating point.
SDP solver behind?
So the SDP solver behind, so here it's MOSEC, but you can also use plenty of other solvers. I think you can also use SDPA GMP, but everything before and after will be only in double. But they are working hard on that to get arbitrary precision, I guess. I know that Lorenzo is also harassing these people. Yes? No?
And can you explain the name of the function CS, TSS,
Oh, yes. So it's a bit verbose. So this is the combo. So this is correlative sparsity, term sparsity, SOS. First, because this is the one on the left. Okay, so now we saw what happened with correlative sparsity, and then we will see what happens if we start with initial term sparsity graph and we add more and more edges. And you will see that the bounds will improve. So here I just apply term sparsity. There is no correlative sparsity. And I take the maximal chordal extension operation. So TS2 is the value of the bound. So here there are 14 affine constraints instead of 35 in the dense case. So again, the bound is quite bad. It's 0 instead of 0.84. But then I can go higher to in the term sparsity hierarchy. And so to go higher, there is a command which is called tsos higher. Then I get the same bound. So I get the same bound, but this is I have a sparse decomposition, and I have only 14 constraints instead of 35 in the dense case. And then you can still go higher if you want, or not. And then the solver tells you no, you can't go higher. So the decomposition that I obtain here correspond to the final iteration, and so should correspond also to the decomposition given by sign symmetries. So here there are some sign symmetries in this problem. So for instance, flipping the sign of x3 leaves the polynomial invariant. Also simultaneously flipping the sign of x1 and x2. Any question on that? Yes.
You said that the bounds you get with the circles are bounds up to the intervals, right?
Oh yes, of course you cannot trust this.
Yeah, and so do you have any way of getting bounds?
Yes. Yes. So if your decomposition lies in the interior of the SOS cone, then you can perturbate a bit your constraints in your SDP and obtain exact decomposition. So have an exact equal sign here.
I mean, how do you do that with the tools?
You do a post-processing. So you take this approximation of the true SDP matrix, and then you project it on the set corresponding to exact equalities. So if you are in the interior of the cone, then you can always do such a projection. And of course, your numerical precision needs to be high enough so that the projection doesn't ruin the process.
And do you provide an implementation of this?
Yes, so this is what we developed with Moab. It's a Maple software called Real Certify. But we only developed this partially here because of the same issue that you asked, that we don't have rational coefficient polynomials in jump. Math opt? Moment tools, but moment tools is not rational, right? Oh, yeah. There is also the software by Bernard and Laurent. But so you can take rational. Mm-hmm. Okay. Okay. Yeah. Of course. No, it's not the same size. It's so it's smaller because basically you exploit the sign symmetries. It's the same bound as a dense symmetric sign symmetry exploiting case. Okay, and then there is a similar thing in the non-commutative case. Where here, so again, we have the running intersection property. We are in the constraint setting, and then you don't have necessarily a sparse sum of squares. So I will just finish the course with something that I find nice. So who doesn't know about Motzkin polynomial? Okay, so this is a very famous polynomial because this is maybe the easiest polynomial, which is known what? Huh? Which is known to be non-negative, but not a sum of squares. So how do you prove that this guy is non-negative? Florent, how do you do that? Huh? What? Ah, sure, yeah. You solve the infinite dimensional problem? No, you just use. Yes, it is. It is. That's a nice way to prove it, but maybe less sophisticated. Exactly, arithmetic geometric inequality, where basically you take the two first terms, the high degree terms, and 1. Then you take 1/3 power, and then just realize that it gives you f is non-negative. And then how do you prove that it is not a sum of squares? Well, it's funny because if you look at the original proof, they made a lot of cases on all possible supports, and so it's very complicated proof, so you have lines of computation like that. But actually the proof is very elegant if you use this Resnick's theorem. So here I have 4 points in my support. Maybe you don't see them, but they are here, here, and here. So I get the triangle after taking the convex hull, and then you shrink the triangle by 2. And then you have 4 possible points in the support of the square. Okay? By Resnick. And then you say, okay, so it's a sum of squares, and each square must be a linear combination of these 4 points. Okay, so 1, 2, 3, 4. And then you say, okay, but then I have a problem because how do I get -3? It's impossible. It's impossible because to get x1 square, x2 square, you need to square this guy. This is the only way to obtain x1 square, x2 square. And then you must have c square, and it's impossible because here you want -3. So on this I will finish. Thank you.
So thank you, Victor. There have been many questions. Are there more questions?
Yes.
So you mentioned at some point, so there were some examples where you had, you didn't show, but you have the bad accuracy, like 15%. It was for combined sparse and...
for the optimal power flow problems, maybe.
Yeah, for one of them.
Oh, I didn't show them, but I have also bad results.
But my question is, so is there a way to improve the accuracy, for example, by mixing with subdivision approaches?
Yes, of course. So I did that, for instance, during my PhD. Because at some point you don't have a choice, right? You can't go higher. So you can do for instance, what physicists do is that you take random support. So you take random terms and you index your matrices with these random terms up to the limitations of your computer in terms of memory. And then if you have more CPU, then you can do the subdivisions as you say.
But in this example, though, the dimension is very big. So
yeah.
So do you have some way to guide the subdivision in those cases?
No. And I've asked to the people from this RT company, because they claim that they have branch and bounds techniques, but seriously, I don't understand how they do the branching.
Thank you.
Any other question? No? Sure. Let's thank Victor again.
Thank you.